So, in the last class we have introduced just formally the convolution of two functions. So, what we are going to see is that its validity and where the convolution is defined and which spaces, and eventually that are all required. So, in this couple of lectures we will do various spaces where the functions belongs to and then the convolution belongs to. So, just recall what is then the thing. So, for two functions phi and psi, we have defined formally the convolution of phi star psi is equal to phi of x minus y psi of y dy, which is by translation change of variable, translation invariant, same as y phi of y psi of x minus y dy. So, that gives you the commutativity if x is the so, you eventually see that convolution is a smoothing operator in the sense that you can use this to define smooth approximation. And one simple estimate what we have seen yesterday is that we are going to see this more if phi is in L1, and first thing is this one, if phi and psi are continuous in Rn and one of them is compact, suppose then integral of a continuous function in a compact set for in the definition of phi star psi it is well defined. And if phi is in L1, the other one we will, as I said, we will see more, and phi is in L1 is psi is in L infinity and then phi star psi is in L infinity. We are going to see soon that it is true for any LP, and then you get this estimate. So, this actually implies that norm of phi star psi in L infinity is less than or equal to norm of phi in L1. That is the same thing, L1 into norm psi at L infinity, you see. So, and if both of them have compact support, so you also have support of psi, phi star psi is nothing but support of phi plus support of psi. So, what we are going to immediately quickly say that if you have three functions and if these two products are well defined and then they are equal and well defined as we will see that one. So, let me quickly give a proof of that. Proof is easy, that is associative, the convolution is associative. Okay. So, let us write down. So, I am not checking about its validity, but then assume that all the integrals are well defined, eta x. Okay. So, first you take convolution of that is same as integral of Rn, okay, phi star of psi at y into eta of x minus y dy. Now, you write down that one is in Rn, we may not write all the time. This is integral again over Rn, phi of z, so to write down, and psi of y minus z dz of eta of x minus y dy. So, you apply Fibini, you get integral over Rn phi of z, okay, this one integral of Rn again psi of y minus z eta of x minus y dy of dz. So, you make a small, this is by Fibini, as and when it is true. Now, make a small change of variable, you define y minus z is equal to t, then you substitute for your y, that is the integral term, that is integral over phi z, of course in Rn, of integral of Rn of psi of t eta of x minus z minus t over dt of dz. And look at that, this is nothing but phi of z, and what is this? This is nothing but your psi star of eta evaluated at x minus z is of dz, and that is nothing but phi star of psi star of eta at the x. So, you have that proof immediately. Okay. So, now we will go to the next theorem. If the previous theorem we proved for L1 and L infinity, now we are going to prove it for the general case theorem. This I will try to give the proof, but then there are some more general theorem which I will only write. Let phi is in L1 means L1 of Rn, and psi is in LP, psi is in LP, okay, 1 less than or equal to p less than or equal to infinity. For infinity case, p equal to infinity case we are already seen and it is easy, okay. Then phi star psi is in LP, and you have the estimate norm phi star psi at p, p means LP is less than or equal to norm phi at 1, that is L1. So, do not confuse with C1. So, here we are writing L1 if you want, LP into norm psi at LP. Okay. So, how do you do that? Let me give you a quick proof of that. So, first let me prove the case when p equal to 1, okay, case, so step 1 or case 1, p equal to 1 we will do. So, you define this two variable function f of x y equal to phi of x minus y psi of y. This is hard to measure, these are all you already learned it in measure theory. If phi and psi are one variable measurability, this is R2 Lebesgue measurable. You should know the measurability. Okay. So, what do you do is that I am going to compute this. So, this is Rn, this is Rn, modulus of a, once it is measurable you can always, this is, you can do this one, dy of dx, you see, and this is non-negative. So, this integral it may be possibly infinity, but we are going to show that it is finite. Okay. So, you substitute this one in double integrals and then you apply the inequality. So, you will get integral of psi of y, I will write this one first, or apply the Fibini, whichever integrals you are taking. So, you apply Fibini and bring it outside, and then you can take the modulus here. So, everything is in the modulus case, and you have integral of phi of x minus y dx of dy. Here is one observation you always have to do, how to get rid of the variables. Now, you see this is Rn, you are integrating with respect to x, but this is a translation invariant. So, this will be the same as integral of Rn modulus of phi of x dx. If you want, you can use another variable, like, because this is by translation invariant, put x minus y equal to t, your dx equal to t. So, it is a phi t dt translation translation invariant, okay, of the Lebesgue measure. These are the invariants. This is the properties you are using, variance of Lebesgue measure or change of variable formula. So, once it is done, this is a two separate integrals. So, you can take this out. So, you get and so let me write it, and that you take it, this is nothing but norm phi at 1 L1, you see, and then you have integral of mod psi of y dy. You are able to take that out of that, okay, Rn, and this is norm psi at L1 because p equal to 1. So, norm psi at 1, and this is phi is in L1, psi is in L1, p is the case. So, this is finite. Okay. If that is finite, what does that, an integral over Rn So, this is your one integrand. So, that implies if the integral is finite, integrand is finite almost where that implies integral of modulus of f of x minus y dy. This is keep this in mind, okay, is finite almost everywhere. That implies immediately this integral of x phi star of psi at x. This is with respect to y, that is equal to phi of x minus y c of y x's. Of course, everything in the almost everywhere sign, and further norm of that all follows from just one thing, phi star of psi at L1 is less than or equal to integral of this integral. You see, that is same as this integral, less than or equal to modulus of. So, this you write it integral of phi star of psi x that one step I have skipped it. So, dx. This is less than, because this is phi star of psi L1 is integral of phi star of psi modulus of that modulus is this estimated with this, okay, and that is estimated from here. So, this implies less than or equal to norm phi at 1. So, you have phi at 1 and norm psi at 1. So, that case is fine. So, step 2 slightly more not really complicated, but you have to be little more carefully. So, what we have to prove? To prove basically you have to show that 1 less than p less than infinity. So, case p equal to 1 is over, case p equal to infinity is over. So, to prove that phi star psi is in LP. Now, we use representation theorem, we use Rees representation theorem. That is what we are going to do. Representation and define, we are going to do that and define phi star defines an element in defines, and that is enough, an element in LP dual. That LP dual is nothing but your LQ. Okay. So, you do that, you view. So, that is a Rees representation theorem. To see it in LP, you see that it defines a continuous linear functional in the LQ dual, where 1 by P plus 1 by Q. These are all some interesting proofs equal to 1, and that is well defined here. So, what you do is that here, so to do that, it is I have to define a linear functional using phi star psi. Even because phi star psi is not defined yet, we do not know. So, you can't just use that integral. So, you have to be carefully do that one. So, you take theta in LQ and define f of xy, define f of xy equal to phi of y psi of x minus y. You can take x minus y over here, accordingly you have to take the integrations properly, okay, theta x. Again this is measurable, no problem, measurable in R2, and we compute the same thing. So, we will compute in double integral modulus of this, we can always do. Once it is measurable for non-negative functions, you can define this will be dy and this will be dx. So, there are 3 terms here, and first dy and then dx is equal to. So, you do apply this one and apply the Fibonacci etc., and then you estimate. That is a standard trick. You get integral modulus of theta x and then integral phi of y psi of x minus y modulus, everywhere modulus you can apply, modulus dy of dx. Okay, you do. Now, what you do is that this is thing you apply Helder. What you get is that this term will be less than or equal to mod phi power p. F is in keep that in mind, okay. Now phi is in LP. Now which one you want to apply? Oh, sorry, something wrongly I have done. Sorry, I have to change. Then there we are not doing actually anything. So this is not what you. Yeah, these are all Fibini appropriate apply. Phi here and theta here. Okay, so that's what you have to. So theta, yeah. So this I have a change of variable. Theta. Both are correct, but then I will not be able to apply properly. That's all. Okay, here this is theta x and phi of y here. Okay, phi of y there. I want phi here outside, and because theta and psi are conjugate. Okay, so theta of x and x minus y here, this will be dx and this will be dy, this will be dy. Okay, yeah, now that is correct. So you have to take the parameters correctly. Okay, so this will be theta is in LQ. So this is in LQ. So this will be theta power q whole power 1 over q and integral of psi of x minus y power modulus of p. This is with respect to dx, keep that in mind, dx, and again apply change of variable or translation. You see, after doing this you apply translation. So you have to apply correctly. So this will be norm theta at q into norm psi at p, because you can apply translation. So that will come out and then you will get norm phi at 1. So this will be less than or equal to norm phi at 1. Take this out. So we will get norm phi at 1, norm psi at p into, I write it bracket purposefully because it is the linear operator we are going to come. So you can apply the same trick. So this is finite now. Again the integrand is finite. You can see that this implies this portion is finite almost everywhere. So okay. So if once this integral is finite almost everywhere, that immediately that's my basically with theta is my convolution product him. So you can define a linear operator. So I have a linear operator T from LQ to R given by T theta for every T theta is equal to this integral, double integral f of, because it is finite, dy of dx. And what the above estimate implies you that modulus of T theta is less than or equal to some constant. Your constant is this one, you see, 1 into norm psi at LP, okay, into norm theta at Q. That implies that T is a continuous, T is continuous. Linearity of course, bounded functional, that gives you the bound, and norm of T is less than or equal to norm phi at 1. Okay. This is precisely, so the proof is complete. If some points are missing, you can just compute that one. So now apply Rees representation theorem. You know that every continuous linear functional can be identified with the element of LP. So, this is T is a continuous linear functional in LQ, and you can identify it with a element, and that element is precisely your definition of phi star of eta. So, Riesz representation theorem. Okay. Okay. Riesz representation theorem implies the existence of this phi star of psi is in LP and phi star of psi at LP less than or equal to norm phi at 1 plus norm psi at P. So, that is all some your elementary functional analysis and application. It is a very good application of your duality of LP and LQ. Okay. Yeah, that completes that proof. So, there is a more general theorem which I am not going to prove it. You can refer any books where it is available. What is called Young's inequality. This is also useful and is more general. Okay. So, we have gone step by step. Young's inequality, it is for more general thing. So, let 1 less than or equal to P, Q, R less than infinity, and 1 by P plus 1 by Q is equal to 1 plus 1 by R. Okay. So, P, Q, R any numbers satisfying this inequality. If of course, if R equal to infinity, this is 0, this is 1, that is different. Okay, which you know that. Phi is in LP, Q, psi is in LQ, then phi star of psi is in LR and norm of phi star psi at LR less than or equal to norm phi at P, LP norm, and norm psi at LQ. Okay. So, we will skip the proof. So, you can refer. It is nice to see the books and see the proof. Okay. So, I have some more time. So, I want to, I do not know what, some of the things I probably skip it, but let at least start stating it one by one. There are very few things to do it. So, maybe one more. These are all important things, theorem about the smoothing effect. Okay. Okay. So, suppose Fg continuous on Rn having one of them compact septum, having anything one of them compact support, then you know that, right. Phi star is already defined, which we already told you, support, because continuous, then integral is only on a continuous of a continuous function on a compact set, and hence it is well defined. If one of them, if one of, so maybe I will use F and G all the time, phi and psi, because we are using that, phi psi are continuous. If one of phi psi, anything, both can be, is C infinity, then you see phi star psi is C infinity. So, it is smoothing, this is called the smoothing effect, smoothing, see smoothing effect. Okay. And you can compute phi C infinity, and you can compute d power alpha of phi star of psi that will be d power alpha. It is enough to take on one side, that is a psi, if phi is C infinity, and it will be phi star of psi d power alpha of psi if psi is C infinity. If both are C infinity, both are same. So, for the derivative to take of a convolution, it is enough to derivatives on one side, and by operating convolving with a, later you will see that when we define more general function, you can convolve with smooth functions to get smoothing, and which can be used even to approximate distributions. That is what you will eventually see this one. Okay. I think I will give a quick proof of it. Verify the steps in case you feel that I am skipping some steps, because we assume certain knowledge and you do the one. So, in step 1, but you write down all the small steps. Those who are studying this course should write down everything, because it is really an application of your functional analysis and measure theory. So, this way by studying this course you will also update your fundamental courses. So, first we prove the continuity of phi star psi. Okay. How do you prove the continuity? So, what do you assume? So, assume one of them has compact support. So, you say that k is equal to support of psi, does not matter. So, you are doing that one. So, let us compute this one, phi star of psi x plus h minus phi star of psi, existence you already know. This will be less than or equal to. So, integral will be over a compact set, the k support. So, it is enough to integrate over a compact set of modulus of phi of x plus h minus y, because phi star psi in x plus h. So, you have to do minus. So, you write down the definitions, okay. Phi of x minus y, this is coming from here, and then modulus of psi of psi. So, if phi has compact support, you just change it and apply it to psi, and then phi and psi interchange in writing this here. Now, phi is, the step is phi is uniformly continuous, because integration is over on compact sets, even if you take either way. Okay. Uniformly continuous on compact sets, okay, given epsilon. So, you apply this basically, there exists delta positive such that this quantity modulus of phi of x plus h minus y minus phi of x minus y, if you are applying the inequality at the point x minus y, keep all that in mind, small changes, is less than or equal to epsilon for mod h less than or equal to delta. So, by choosing h small enough, you can make this small, that is what it is saying, make small. Once that is less than epsilon, you can take it out, and then psi is an integral of psi over over k, and which is a finite quantity. So, basically this integral is small. So, as h tends that implies as h tends to 0, okay, h tends to 0, phi star of psi x plus h tends to phi star of psi x, proving the continuity. Okay. Okay. To look at the differentiability, more or less similar trick, next step, differentiability. It is enough to prove for alpha equal to differentiability. It's then it is enough to prove, then you repeat it whichever direction you want. prove for alpha equal to 0 0 at the ith stage you take 1 0 etc. That means we are so we are computing d by dxi of phi star of psi, okay, at x. That is all we are trying to compute now. So, you have to only check the validity, nothing more than that. The same principle. So, for h small compute this 1 over h phi star of psi at x plus h e I. That is how we want to compute it, phi star of psi at x, and then you have to see h tends to 0. This is you can compute this again is equal to 1 over h integral over k, and then you get the same thing phi of x plus h e I minus y minus phi of x minus y psi of y dy, okay, psi of y dy, and this can be written as 1 over h phi is so you assume here, so you start one of them, so assume phi is in what do you say C1. So, that is what you are assuming, and if you want alpha, assume phi is in C alpha Cm of mod alpha less than or equal to m. So, this will be nothing but your d phi by dxi, okay. So, make things clear at any point. If you are not clear, you have to x minus y theta some h e I into psi of y here. Yeah. What you have to do is that, so d phi by dxi is given, this is over k, d phi by dxi is continuous on k, and that implies it is bounded, d phi by dxi is bounded, okay. So, you have a bounded function here basically, of course 0 less than or equal to theta less than 1 and bounded in k. So, you have a, and psi is an integrable function, okay. This is integrable. So, this is bounded, psi is integrable on k, okay. So, and this 1 over h this goes to, and 1 over h this goes to d phi by dxi at x minus y. So, 1 over h d phi by dxi, this is a point wise at x minus y theta h e I, this will go to d phi by dxi as h at x minus y as h tends to 0, you see. So, you have every setup of bounded dominated convergence theorem. So, you have the point wise convergence together with L1 bound, okay. So, implies dominated convergence theorem. What is the LHS? So, a dominated convergence theorem, so right hand side pass to the limit and the left side the limit exists, and you get d by dxi of phi star of psi at x, right side you get precisely converges to d phi by dxi at x minus y psi of y dy, okay. So, integral of d of d phi xy x minus y psi of y dy, and that is nothing but d phi by dxi at convolution psi at x, okay. So, that proves that you can repeat this. After that, any derivative you can keep on repeating if you have more about it. So, yeah, I will stop and we will continue to do more results on that and including the density arguments. So, we will stop and then we will continue. Okay. Thank you.